Welcome back to VLSI technology lecture. In the last lecture, we have seen the basics of our epitaxy methods and how a various thin film can be grown, in which we have seen the chemical vapor deposition technique, in which uh, particularly we have seen the vapor phase epitaxy. Now we have to move on to the next epitaxy method, so which is our molecular beam epitaxy, and this particular technique MBE is in particular very much versatile, and nowadays it is very much useful because of it offers certain advantages over the vapor phase epitaxy. So that we have to look at what are the advantages and how epitaxial layer can be grown using the molecular beam epitaxy method. So let's begin the discussion. Okay, so in molecular beam epitaxy, as we have already seen that in case of epitaxy, when we want to grow the epitaxial layer, okay, epitaxial layer, as we said, it should be a monocrystalline layer over a particular wafer surface. Okay, so we will be taking a particular substrate, and onto that we have to grow a particular thin film that will be monocrystalline in nature. So in case of when we have talked about the wafer phase epitaxy, in the case of wafer phase epitaxy, whatever particular material that we want to deposit onto the surface, like in case of silicon wafers, if we want to grow a particular epitaxial layer of silicon, then we had taken a particular source of that particular silicon, and that will be sent to a growth chamber in the form of vapors, and then a certain chemical reaction took place, and then a particular layer can be grown over the surface. But in case of if we talk about the molecular beam epitaxy, in this case we do not send the vapors, and there will be no chemical reaction going to take place onto the wafers, but rather what we have to take is we have to take a particular source of material. If it is a elemental semiconductor, and let us say if we want to grow the silicon, then we have to take the silicon, and then we have to means we have to evaporate it. Okay, we have to evaporate it by hitting it through a very high energetic beams. Okay, high energetic electron beams. Fine. So when we have the electron beams, it will be evaporating, it will be striking onto the silicon, and then it will be it will be heating up to its melting point, and eventually it will be going to be evaporated, and that will be forming a beam of silicon. Okay, silicon atoms, and that will be directed towards the substrate, and then ultimately it will be when the temperature gets down, it will be cooled down, it will be condensed, and then after the condensation take place, this particular silicon atom going to be deposited over the substrate or onto the wafer surface. So basically you can look at what are the different objectives. So basically the objective of this molecular beam epitaxy is to deposit a single crystalline thin films. Fine. And obviously it was actually invented by J. Arthur and Alfred Y. Chuo in the Bell Labs somewhere in the 1960s. And one very important thing that we have to take care about the MBE is the MBE chamber is very ultra high vacuum chamber. Okay, you remember this. This is the ultra high vacuum chamber. So it means the pressure is very low, very ultra high vacuum. Okay, we are talking about the vacuum. It is a order of 10 to the power minus 8 Pascal. Okay, of the order of 10 to the power minus 8 or minus 10 Pascal. So it is an ultra high vacuum that we have to create. Okay, and remember this task is not easy to achieve such a ultra high vacuum. So that we have to look at how it will be achieved, and what are the difficulties. Okay, so that we have to keep in mind. One more important parameter is that in the molecular beam epitaxy, the growth rate can be achieved very small, okay, very small deposition rate, or you can say the growth rate can be achieved like we have written here, like 1 micron per hour. Okay, so you can say that it is even 0.01 micron we can grow per minute. Okay, 0.01 micron per minute we can grow. So this is a really advantageous because we can have excellent control over the thickness of the layer which is going to be grown. So thickness can be controlled very, very precisely. So this is one of the very greatest advantage that our molecular beam epitaxy is actually offering. Fine. So now slowly we have to move on to this topic, and we have to look at the different parts. What are the different various parts that we have in this particular MBE system, and what are the use of those particular parts? So this is one of the picture I have taken from the book. Okay, so this particular MBE system is a very complex system. Okay, it is very complex in nature, and not only complex, it is also very costly. Okay, it is very costly. So we have to look at the details of this particular uh, MBE system. So here you can see that we are having a different chambers. Here you can see we are having a different chambers. Okay, so basically in this chamber, you can see here it is written as the beam sources. Okay, so here it is a beam sources. So basically this beam can be a material whose epitaxial layer we want to grow, as well as the dopants. Okay, so within this chambers beam sources, okay, these chambers are actually called as effusion cells. Okay, it is called as the effusion cells, or you can also call it as a Knudsen cells. Okay, these are the Knudsen cells or effusion cells. So within this effusion cells we have to put our dopants. Okay, various type of dopants can be kept within this effusion cells, and also we can have a chamber within which we can keep our material whose monocrystalline layer we want to grow. Okay, so these are the different chambers. Now we can see that there is a mechanical shutter, you can see. Okay, here is the mechanical shutter. So the function of the shutter is to open the mouth of these chambers. Okay, so that this if beams we are, if we are keeping any dopant material over here or any other material in this particular chamber, if we are heating it by a certain mechanism, and when it is getting evaporated, if we open the shutters, then it will be allowed, this means open, once we'll be opening this one, then it will be allowing this beam to go towards the substrate. Okay, so somewhere in the system we have to place our substrate, and towards this substrate these beams only can go once we open the shutter. So this shutter will be acting like a control mechanism. Okay, so if you completely open the shutter, obviously the entire beam is going towards your substrate, and if you want to turn it off, obviously we cannot turn it off instantly, because we know that because of very high temperature within the effusion cells. Okay, this temperature cannot be reduced certainly. Okay, it will take a finite amount of time. So if such need is arises, let us say we want to stop it instantly, then what we have to do is we have to close the shutters. Okay, the mechanical doors. So once you will close it, it will not allow the beam to pass it through, and it cannot reach to the substrate. So that we have to keep in mind. So these shutters will be used. It is a mechanical shutters, and it will be operated by microprocessors. Fine. Here you can see lots of other, like here you can see a cassette entry. Okay, lock. So within this entry, what we can do is through this entry we can place our substrate. Okay, either a single substrate or multiple substrate can also be placed within the chamber for growth. Similarly, we are having a certain other mechanisms, like here it is written as RHEED screen, read screen. Okay, so these screens will be used for the characterization of the grown layers, whatever layers we are going to grow. that will be characterized by having or by seeing the read patterns. Okay, so RHEED is actually stands for reflective high energy electron diffraction uh, patterns. Okay, so that pattern will be telling you what are the quality of the grown layers, so that we have to keep on monitoring whenever we are growing the uh, our monocrystalline layer or epitaxial layer. Fine. Here we are again showing certain analytical facilities. So we do have a certain other characterization facility that is attached over here, and that can give you another features of your grown epitaxial layer. Right. So now we have to move on, and we have to look at, this is really a very complex picture, and we have to look a very simplified schematic diagram for this one. Okay, and then we have to look at what are the various processes by which we have to go through, and then we have to grow a particular epitaxial layer by following the molecular beam epitaxy. So this is one of the simplest schematic diagram whatever we have seen in the last slide, last picture. Okay, it is a very simplified version, we can say. So in this picture, what we can see is, first of all, you can see here we are having a substrate. Our substrate is somewhere here. Okay, it is a substrate holder within which we are having our substrate. Okay, and then this substrate is actually having a particular susceptor. Okay, this susceptor will be used for heating the substrate. Okay, it will be used for heating the substrate. So here this heating can be like RF induction heating, or we can also go for your the thermal heating. Thermal resistance heating can also be used. Fine. So various heating mechanisms for heating this particular substrate can be used. Normally, what happens is this substrate is normally kept at, as compared to your you can see first the other details. Okay, first of all, we'll talk about later the temperature. So we can see this is our we have already seen this is our substrate. It is actually held by a substrate holder, and then we are having a susceptor which is used for heating the substrate. Now we can see here we are having one of the effusion cell. Okay, we are having one effusion cell. So within this effusion cell, okay, a particular dopant material will be kept. Okay, a particular dopant material, because when we are we want to grow a particular monocrystalline layer, okay, onto this particular substrate, and if we want to have a particular doping profile of a particular dopant, then what we need to do is we need to have the dopant also. Okay, we need to evaporate the dopant also. Okay, so within this fusion cell we have to place our dopant. Okay, desired dopant, whatever we want. And within this fusion cell there should be a certain heating mechanism. Okay, that heating mechanism may be a RF heating, it may be a thermal heating, it may be a radiant heating. Whatever heating mechanism that may be preferred, it may vary from system to system. Okay, but we can have a particular heating mechanism. Okay, that will be heating this particular dopant material such that it will get evaporated. Okay, and here you can see the mechanical shutter. Okay, we are having a shutter. Okay. Similarly, this is one of the shutter, and again we are having another shutter just before our substrate. Okay, so both the shutter together can control the amount of beams that may get impinged onto this particular substrate. So that can be controlled by having this mechanical shutters. Okay. Now, if we want to grow the silicon layer, okay, we want to grow the silicon. Let us say, for example, it can be elemental monocrystalline layer that we want to grow. Like if we want to grow the silicon, or we can also have the compound semiconductor, for example, gallium arsenide. Okay, so we can also have the gallium arsenide. We can have a particular substrate onto which we can want to grow a particular gallium arsenide monocrystalline layer. Fine. So, for example, in this case, let us say if it is having a silicon source, so we will be keeping a silicon source over here, okay, like here. This is our silicon source. So, within this crucible, okay, again we are having a particular crucible. Within this crucible, we have to place our charge, means our silicon will be placed within this particular crucible. Now, as we know that the melting point for our silicon is very high. Okay, it is somewhere around 1400 degrees centigrade. Okay, so to evaporate this particular silicon, okay, thermal heating or the radiant heating is generally not preferred. Okay, so what we have to do is we have to use the electron beams, very high energetic electron beams, and that beams will be hitting this particular charge. Okay, and then this particular silicon will get evaporated. Okay, so that will be done through a electron gun. Okay, so here we are having an electron gun mechanism. It is specifically for deposition of our silicon. Okay, if we want to grow the silicon epitaxial layer, then we need to have this electron gun assembly. Okay, otherwise some other heating mechanism may be preferred if we are having some other material to grow. Okay, but in particular for silicon we need to have the electron gun source. Okay, so basically this electron gun will be actually it will be emitting the electrons, okay, a very high energetic electrons, and then we have to use the electromagnetic focusing method. Okay, so electrons will be emitting and then it will be going towards the this particular charge, towards this particular silicon, and it will be bombarded upon the silicon. Okay, so once the bombarding is done, then it will be heating up and then it will emit the silicon beams. So you can say it is the atoms which is getting evaporated. Okay, and then after evaporation, it will be emitted and it is going towards this substrate. Fine. Its design is such that it will be going like this. Okay, towards this direction. Okay, towards this substrate. Then what happens is we can see once we turn on the electron gun. So before all this operation to begins, okay, before that we have to first let's start. First of all, what we need to have is before starting all the procedures, okay, what we have to do first, we have to evacuate this chamber. So what is our need is first we need to achieve the ultra high vacuum. So ultra high vacuum means the pressure within this should be up to the order of 10 to the power minus 8 Pascal or 10 to the power minus 10 Pascals. So this should be the range of ultra high vacuum that we need to achieve. Okay. So you can see here we are having two pumps. Okay, titanium sublimation pump and another is a turbomolecular pump. Okay, so this we have to achieve first. Okay, before starting anything, any process, we have to first evacuate the chamber and we have to achieve the ultra high vacuum, because molecular beam epitaxy will take place within the ultra high vacuum. Okay, otherwise other gases will be present and it is going to be contaminate your uh, this particular wafer surface. Okay, and not only that, if other molecules are available within this, then it is also going to deviate the these paths. Okay, if it is getting ionized because of the high temperature, it will contaminate. Okay, it will not have the proper beam emissions and it is not going to strike onto these surfaces. It may be going somewhere else. Okay, so we need to evacuate it properly. Okay, proper evacuation is needed. Fine. So basically to achieve this ultra high vacuum, this is a very difficult task to achieve. There are so many pumping method by which we can evacuate the chambers. For example, we are having the rotary pumps. Okay, we are having the diffusion pumps. Then we are having a like uh, liquid nitrogen cooled adsorption pumps. We are having the cryo pumps, we are having the turbomolecular pumps, we are having so many pumps. Okay, so but in the case of molecular beam epitaxy, we generally do not follow the rotary pump or diffusion pump because those pumps are having certain oils. Okay, they are using certain oils because of the some back diffusions or some disadvantages. Okay, we do not prefer that one. Okay, so certain combination of some other pumps, like in this case you can see the turbomolecular pump or some titanium sublimation pump. Okay, these pumps together will be used first to evacuate the chamber, and normally to achieve this ultra high vacuum it takes so many days. Okay, it doesn't like it can be achieved within an hour or within a day. Okay, it will take few days to evacuate a chamber and to achieve the ultra high vacuum. So it will take a lot of time. So just achieving a ultra high vacuum is not the only thing. Okay, once we achieve the ultra high vacuum, we again we have to uh, maintain it. Okay, anyhow we should not like that once we have achieved it and by once we are moving from one run to another run, this ultra high vacuum should not be disturbed. Okay, if it is getting disturbed, then we have to wait for a long time to go for the another run. Okay, so we have to maintain the ultra high vacuum also. That is also very much important, so that we have to need to take care of. So first of all, we need to evacuate it, and then in the next process, what we have to do is we have to place our substrate into the chamber. Okay, so we have to uh, place our wafer or substrate into this particular chamber. Okay, so we have to keep in mind that while placing this particular substrate within the chamber, okay, uh, its ultra high vacuum condition should not be broken. Okay, should not be broken. If it is getting broken, then again it will take time to evacuate it. So that what we have to do is while placing a substrate within this particular system or a chamber, MBE chamber, one system which is called as the load lock system is actually used. Okay, so there is a mechanism by which if we are keeping our substrate through our load lock system, then load lock system is designed such a way that if we use this system after placing the substrate, that substrate can be placed within the chamber without breaking the vacuum condition. Okay, and that way we can place our substrate. So once we place our substrate, now as we know that when we want to grow a ultra high pure monocrystalline layer of our epitaxial layer, then before that what we need to do is, as we already seen that our wafers or our substrate is containing a lots of contamination and damages. Okay, so we need to means we need to correct them. Okay, we need to remove those contamination, we need to correct the damages, or we have to remove those damages. Okay, before we start any further processing, or we are going to make a particular layer. Okay, to grow, before growing this epitaxial layer, we have to remove those contamination. Okay, so naturally, as we said, in this case, we are not having any chemicals. We could not place any chemicals inside, and we cannot have the chemical reactions. And we have seen that in the wet cleaning system, dry cleaning system, even we do have lots of chemicals involved. Okay, and then only we can means clean our vapor surface. But in this case, in the MBE case, what we have is, see, whenever we have a cleaning mechanism within the system. Okay, if we placed our wafer inside, and then if we want to have a mechanism by which we can clean the wafer, it is called as the in situ cleaning process. Okay, it will be called as the in situ cleaning process. If there is no mechanism on site or within the system, if we have to place the wafer outside the system and only outside the system it can be cleaned, it is called as the ex situ process. Okay, so basically what we have to do is, first we have to evacuate, we have to achieve the ultra high vacuum, and then we have to place the substrate using the a load lock system, and then we have to go for the cleaning of the substrate. Okay, in situ process, in situ cleaning we have to perform. So to perform the in situ cleaning, what we can do is we can go for a very high temperature baking of this particular substrate. Okay, so what we have to do is we have to raise the temperature up to 1000 to 1200 degrees centigrade. So if we raise the temperature at very high, then its surface will get automatically cleaned. Okay, so that way we can do the cleaning after raising a temperature at very high. Okay, so that is one of the way how we can clean the surface. Okay, and the second way is we can do the sputter cleaning. Okay, in the sputter cleaning, what we have to do is we have to take the organ gas, any inert gases, and then the beam of the organ will be bombarded onto that. Okay, and because of the bombardment there may be a chances of damaging the surface, but that bombardment will be followed by one process again which is called as the annealing process. So within the annealing process, again what we have to do is we have to again heat up the uh, temperature of the substrate up to 800 degrees centigrade or 900 degrees centigrade, and that way we can again recover those damages and we can clean the surface of the wafers. Okay, so that in situ cleaning we have to perform first. Okay, either baking it at vacuum, very in a vacuum at very high temperature, or by having the sputter cleaning. Okay, and this way we can clean the surface first. Okay, that surface will be get cleaned. Now once the surface get cleaned, now we have to go for the deposition of the layer. Okay, so how it can be done in the case of silicon, as this is the most simplified picture of our MBE system. So what we have to do, we have to start the electron gun. Before that we have to load this crucible with the charges. Okay, a particular charge, like in this case it is silicon, then a particular dopant material has to be placed within this fusion cells, which is also known as the Knudsen cells. Okay, so in these cells we have to place a particular material. Now we have to turn on the electron gun and we have to use the electromagnetic focusing method, and then this electron beam will be bombarded onto this particular silicon and it will get evaporized. Okay, so once this evaporation is taking place, at the same time this will also get vaporized by some other heating mechanism. Okay, so some other heating mechanism may also be used. Fine, and then this two beam will go together, and then it is going to condense onto this particular surface of the substrate, and slowly it will be forming a layer. Okay, and because both these atoms is going to interact, okay, and then it will deposit it onto this particular surface. It is not having any chemical reaction, but it is just going and then condensing, and because of the condensation it will get deposited. So what we are doing is we are growing both the silicon layer, and this silicon layer is now going to be deposited with the particular dopant material. Fine, so that can be achieved in this particular fashion. Now we can see that behind this particular substrate, okay, we also have a thermocouple, a mechanism that will be keep on monitoring to the temperature of our substrate. What is the temperature of the substrate? So whatever be the required temperature that we need, that temperature can be keep on monitoring by a thermocouple. Okay, now we can see that because we are evaporating the atoms. Okay, so these atoms composition, okay, these atoms composition can also be monitored by this mass spectrometer. We are having another device which is attached with this particular system, which is our mass spectrometer. Fine, so this mass spectrometer will be keep on measuring the composition of the evaporated atoms. Okay, evaporated gases you can say. So it will be keep on measuring the composition. So by seeing this one, we can give a particular feedback to this particular systems. Okay, because this is all microprocessor controlled, so that the composition of each and every element can be controlled. Okay, either we can control the mechanical shutter or we can also control the temperature within the fusion cells, fine, so that the rate of emission of this particular dopant material and the our epitaxial material, that can be controlled. Okay, so that can be used by having this mass spectrometer. Now, as we know that as we said, doping can also be done by having the uh, like our diffusion method and ion implantation method. We have two different methods. Okay, so let us say uh, if we want to uh, do the doping using the ion implantation method, then we have to use this ionization gauge. This is nothing but our unit of ion implantation. Okay, if we want to do the doping not by using the fusion cells but rather by using the ion implantation method, then this ion implanter will also be integrated within our MBE system. Okay, so this ionization gauge will be used for the ion implantation for our dopants. Okay, so that can be used here if we want it. Otherwise, it cannot be used. Fine. It will be depending on what kind of doping you want to perform. Now, uh, as we know that while growing this particular epitaxial layer, we have to keep on monitoring the quality of the grown layer. Okay, whatever the layer we are growing, whatever the thickness. Okay, so that quality of the layer can also be monitored by having a RHEED mechanism. Okay, as you must have seen in the last slide. Okay, so there were one mechanism, one particular thing was attached, that is called as the RHEED patterns. Okay, RHEED screen. Okay, so in that screen, what we have to do is, it is a reflective. RHEED is stands for reflective high energy electron diffraction. So we have to keep on monitoring the pattern of this RHEED. That will be tell us about the growth, the quality of the growth uh, layer. Okay, the grown layer, whatever we have, that quality we can keep on monitoring. Okay, and similarly we can also monitor the thickness. Fine. So this is all about this system. It is a very simple picture of our basic system. Okay, so whatever we have explained is, we have to first we have to go for the ultra pure elements. We have to keep within this nuts and cells. Okay, and that should be heated first. Okay, is heated, it will start to sublimate. Okay, and then this gaseous elements will be condensed onto the wafer, and then it will form a particular layer. So here I have written for the gallium arsenide, but this system is actually, here I am explaining about the silicon. But we can have the different multiple chambers we can have. Okay, so that we can see in the next picture. Okay, so we can have, this is the more detailed diagram. Okay, so in this diagram you can see that we are having a large number of chambers. Okay, lots of chambers are there. Okay. If we want to grow the monocrystalline layer of gallium arsenide, okay, onto a particular substrate, then we need to have these chambers. Okay, you can see it is a resistance setting method we are using within this fusion cells. We are having the gallium, then we are having the dopants. Okay, then we are having the arsenic material over here, then we are having the aluminium over here. Okay, so this way we can keep our different sources. Okay, that sources can be means anything that we want to grow. Okay, that we want to dope. So that way we can place a large number of materials in this particular diffusion cells, and then it can be heated up to a particular temperature to evaporate the materials. Fine. So this way we have to perform our this particular uh, molecular beam epitaxy. Okay, so now one more thing that we have to keep in mind, this fusion ovens. Okay, these are actually called as, also called as diffusion ovens. You can say it is diffusion cells, you can say it is called as the nuts cells also. Okay, these are the different names that this particular chamber got. Okay, so this is actually made up of pyrolytic boron nitride. Okay. This is made up of pyrolytic boron nitride. If we are we want to go for the 3-5 growth, okay, elemental compound semiconductor made up of group number 3 and group number 5. Okay, if we are going for this growth, then like gallium arsenide, okay, so that should be made up of this pyrolytic boron nitride, and it can be of quartz if it is a silicon we want to grow. If we want to go for the silicon epitaxy, then we can have it of the material of quartz. Okay, so that we have to remember. So this way we can obviously we have to keep it the ultra high vacuum. We have to keep it within the system, and we have to particularly control the temperatures. Okay, we have to maintain the ultra high vacuum, and we have to control the temperature so that we can get a particular evaporation rate. Or we have to either control the temperature, or otherwise we have to control the shutter. Okay, so both ways we can control the amount of molecule which is going to impinge onto this particular substrate, so that this evaporation rate can be controlled. Now, one more thing is like RHEED pattern, in which we are going to monitor the quality of the grown layer. Okay, that will be basically used for the research purpose basically. But in more commercial products, okay, when we are going for the commercially doing certain MBE for epitaxial layer grow, then generally we are more interested into grow a uniform layer. Okay, uniform layer of the uniform epitaxial layer onto the substrate. And to achieve that one, what we need to do is we have to keep on rotating this particular uh, substrate holder, so that the substrate can be keep on rotated, okay, to uniformly grow the layer. So what we can have is its doping will also be uniform, and its thickness will also be uniform within this much of variation. Only just plus minus 1% doping variation you may find, and plus minus 0.5% in the thickness variation you may find. Otherwise, we can get excellent control. It is having a very uniform thickness of the layer can be achieved by having this particular technique. And a very thin layer can also be grown. Okay, a very atomic layer can be grown, because a very small layer, you can see the deposition rate in the case of molecular beam epitaxy is very small. Okay. 0.01 micrometer per minute, or you can say 1 micrometer per hour. It's a very small time. Okay, you can assume it. It's a very small time, a small thickness. Okay, a small thickness. So such a small thickness can be achieved. Okay, very accurately can be achieved. So similarly, we can accurately control the doping profile also. Okay, so that's why MBE system is preferred, where accuracy is very much important. Okay, wherever the accuracy is very precise control of these parameters are very much needed, there the MBE system is preferred. Fine. So now we can have our equation for the molecular impingement rate. Okay, so this molecular impingement rate is phi is actually given by this equation. Okay, that could be derived easily. Okay, so phi is equals to p into 2 to the power 2 pi into 2 pi mkt to the power minus 1 by 2. And if you substitute the values of Boltzmann constant, okay, and if you multiply it, okay, with the mass of molecule in kgs, and if you do this calculation, you will be come up with this particular equation: 2.64 10 to the power 10 p upon root over m uh, over t. Okay, so root over mt. So this molecular impingement rate is actually giving you how many molecules are actually impinging onto this particular substrate area per unit time. Okay, so that will be going to decide you what is the thickness of your growth, or you can say what is the growth rate. Okay, so that is finally going to decide the growth rate. So you can see that this molecular impingement rate is directly proportional to uh, the pressure within this particular vacuum. Okay, and it is inversely proportional to temperature. It is inversely proportional to root over the temperature. So this equation will be used for deciding the molecular impingement rate. Now we can look at the certain advantages of the molecular beam epitaxy. So basically what I said is, in this case generally this heater or this substrate is kept at low temperature as compared to this diffusion cells. Okay, this diffusion cells based on the if it is a silicon, then obviously we have to use the electron gun, and because of the electron gun this evaporation of the silicon could be taken place. But for the other material, the temperature within this diffusion cell will be kept low, and as compared to these diffusion cells, this substrate will be again as compared to these cells, this temperature must be low, so that the condensation will take place. Okay, so generally this MBE system is like this substrate temperature is somewhere around 400 degree centigrade to 800 degree centigrade typically. Okay, and it is referred as a low temperature process. Okay, this is one of the advantage, okay, of our molecular beam epitaxy, that it is a low temperature process. The second advantage is, which is very obvious, is we can have the excellent control over the doping profile. We can control the doping precisely. Similarly, we can also control the thickness of our epitaxial layer very precisely. Okay, so these are the certain advantages that our molecular beam epitaxy is actually offering. Okay, low temperature process, doping profile is excellent. Okay, doping profile. Similarly, it also got some disadvantages. The main disadvantage is that it is a very complex system. Okay, very complex system. And the second one is because of its complexity, it is very costly. Okay, MBE system is very costly. Okay, and the third one is we need to have the ultra high vacuum, which is very much difficult to achieve. So I hope this discussion uh, give you certain views about the molecular beam epitaxy. You must be able to understand. You must be able to follow. Okay, so I hope it must be clear and understandable. So thank you for watching.